The metallurgical genesis of the RS-28 Sarmat begins with the selection of ultra-high-grade stainless steel ingots. These raw materials are stored in a stabilized environment to ensure zero structural degradation before the forging process. Automated manipulators capable of handling tens of tons with millimeter accuracy begin the retrieval sequence. The grippers engage, securing the alloy that will eventually become the missile's primary airframe. The material is transported toward the induction furnace for controlled thermal preparation. Internal temperatures are raised precisely to the optimal forging point, ensuring the alloy's plasticity. Now glowing at nearly 1,200 degrees Celsius, the ingot is placed within the heart of the 75,000-ton press. Precision manipulators rotate the workpiece, ensuring uniform thickness and density across the entire diameter. A final sizing pass ensures the 35-meter-long section maintains a perfect aerodynamic profile. Final laser diagnostics verify the structural perfection of the metallurgical genesis before assembly begins. A massive orbital gantry secures the assembly, preparing to fuse these components into a single seamless vessel. The metal is stirred together at a molecular level, creating a bond stronger than the base material itself. The resulting joint features a refined grain structure, essential for surviving the pressures of hypergolic propellants. Active cooling systems manage the thermal gradient, preventing any structural warping of the massive cylinder. Automated sensors adjust for thickness variations, ensuring a uniform weld across every centimeter. The clamps disengage, revealing the completed section of the Sarmat's primary propellant tank. The vessel of pressure is ready, a testament to the advanced friction stir technology that powers Russia's strategic deterrent. The PDU-99 liquid fuel engine block, a marvel of Russian rocket engineering, is moved into position. Heavy-duty hydraulic clamps lock the engine into its permanent housing. Friction welding creates a seamless bond between the fuel lines and the engine intake. High-temperature thermal gaskets are compressed to withstand the heat of the main engine ignition. Gimbal actuators are installed, providing the missile with its flight path maneuverability. Nitrogen pressure tests confirm the integrity of every seal in the propulsion block. The heart of fire is set. The PDU-99 is now a permanent part of the RS-28 Sarmat. A high-precision robotic installer prepares the master inertial measurement unit for seating within the primary housing. Titanium fasteners are torqued to exact specifications to withstand the high G forces of the boost phase. Redundant power circuitry is integrated to ensure the navigation system remains operational, even under extreme electronic interference. The antenna is fine-tuned for maximum signal reception through the missile's composite outer shell. Precision lasers calibrate the optical sensors against a simulated celestial map. Diagnostic probes verify every electrical connection within the neural architecture for perfect continuity. The cooling system is secured, allowing the guidance computer to operate at peak performance throughout the mission. Sensors continuously calculate the balance, adjusting the placement of each subsequent harbinger to the millimeter. As the bus fills, the Sarmat's capacity for overwhelming saturation of enemy defenses becomes visually apparent. The density of the payload requires surgical assembly, as 15 heavy units are packed into the 3-meter diameter bus. The avant-garde interface is locked into the central spine, finalizing the hybrid payload configuration. Payload integration is complete. The crane detaches, leaving behind a perfectly balanced suite of strategic harbingers. To begin the thermal shielding process, the robotic application arm is calibrated to the precise contours of the Sarmat's nose section. The thermal spray system ignites a plasma arc reaching temperatures sufficient to vaporize ceramic and carbon composites. At a microscopic level, these particles bond to the airframe, creating a unified shield against extreme atmospheric friction. Layer by layer, the coating builds into a robust black body radiator designed to manage the thermal loads of hypersonic reentry. The carbon-carbon composite layers are subjected to intense infrared curing to finalize their chemical bonding. Precision micrometers scan the finished shield, seeking any sub-millimeter irregularities that could cause turbulence. With the thermal shield complete, the massive airframe is prepared for the most rigorous structural stress tests. The RS-28 is secured to a super heavyweight hydraulic shaker table to simulate the violent forces of liftoff. Every weld and joint is monitored as the 200-ton body flexes, proving its structural integrity against catastrophic failure. Before the lift can begin, hydraulic stabilizers anchor the vehicle, ensuring absolute precision for the vertical transition. The powerful erection arm begins its slow, calculated arc, defying gravity with 200 tons of strategic weight. The RS-28 now stands vertical, a monolithic pillar of power prepared for its descent into the hardened depths. With the cradle retracted, the missile is now held solely by the silo's internal hoisting infrastructure. Tolerance is measured in millimeters. Shock-absorbing guides prevent the airframe from touching the reinforced walls of the launch tube. The final alignment sequence begins, mating the missile's base with the ejection mechanism with surgical precision. Hydraulic clamps lock the missile into place, securing it against the forces of nature and the shock of nearby detonations. The cables retract, leaving the Sarmat in its silent vigil. The emplacement is complete. The Titan is home. Precision sensors guide the manifold nozzle, ensuring a hermetic seal with the heavy-duty propellant intake. As the cryogenic fluids circulate, the sudden temperature drop causes immediate frost formation on the external delivery lines. The sheer weight of the 200-ton missile increases as about thousands of gallons of liquid propellant fill the internal reservoirs. Automated safety sweeps utilize laser spectroscopy to detect any trace of escaping volatile gases at the connection points. Fueling reaches the halfway mark, with the automated system balancing the load to maintain the missile's vertical center of gravity. As the primary tanks reach capacity, the robotic manifold begins a sequential detachment protocol. The delivery hardware is withdrawn into specialized bunkers within the silo wall to protect it during the imminent launch sequence. The fueling is complete. The super hardened silo cover begins its slow, inexorable closure. The RS-28 Sarmat is now fully fueled and sealed, standing in a state of total combat readiness deep beneath the Russian steppe. Encrypted firing codes pulse through the internal circuitry, bypassing manual overrides to initiate the launch sequence. The cold launch process begins as the powder pressure accumulator ignites, converting solid fuel into high-pressure gas. The piston plate engages, beginning the transfer of pneumatic energy to the base of the Sarmat. Shear pins fail by design, releasing the final physical connection between the missile and the silo floor. Precision guide rails ensure the massive airframe remains perfectly centered as it accelerates toward the surface. The nose cone breaks the surface emerging from the Earth for the first and final time. The tail section clears the silo, marking the completion of the cold launch ejection phase. Protective covers are discarded, exposing the combustion chambers for the first stage ignition. Main engine ignition is achieved. The RS-28 Sarmat begins its ascent under full thrust, leaving the cradle of the Earth behind. Mechanical latches release, preparing the avant-garde hypersonic glide vehicles for their independent deployment. The deployment sequence begins fanning out the payloads to strike multiple independent targets simultaneously. Orienting for re-entry, the vehicle positions itself to utilize the thin upper atmosphere for aerodynamic lift. The friction generates temperatures exceeding 2,000 degrees Celsius, yet the internal systems remain cool. The airframe withstands immense structural stress while maintaining a precise glide ratio. Encased in plasma, the vehicle navigates autonomously, immune to external electronic interference. Precision sensors lock onto the final coordinates with sub-meter accuracy. A coordinated strike pattern covers the continental area, demonstrating global reach. The RS-28 Sarmat, the ultimate pillar of Russia's strategic nuclear triad and a definitive global deterrence.